All right, welcome back to the Symmetric Crypto Theory session. So we're going to have 4 talks. So the first one is on the tight Primage resistance of the sponge construction. This is work by Charlotte Lefebvre and Bart Menning, and Charlotte will be giving the talk.
Okay, thank you for the introduction. So I will present a result regarding the tight Primage resistance of the sponge construction. And this is a work done jointly with Bart Menning. So here we focus on a generalized version of the sponge construction used for hashing purposes. And it is here based on a permutation. So the sponge operates on a state of size d bits, and it is split into 2 parts. The first one is called the outer part. It is made out of orbits, and R is called the rate. Then we have the inner part, which comprises C bits. C is called the capacity, and this is the security parameter of the sponge. Now, to compute the hash of the message, we first split the padded message into several blocks. Each block comprises orbits. Then we go through the absorption phase, where message blocks are added to the outer part of the state. And after each addition, we apply the permutation on the entire state. Once all of the message blocks are absorbed, we can move on to the squeezing phase, where orbits of the digest are extracted at a time. And between each extraction, we apply again the permutation. So by design, the sponge offers a variable length digest, but here we will restrict ourselves to the case where the digest size is fixed to n bits, and we denote by L the number of required squeeze calls. So there exist several tweaks to this construction, and here we focus on 2 of them, which were both introduced in the context of the photon scheme. The first one allows to have a first message block which is larger, with a size denoted by R prime prime. And in the second tweak, the digest is extracted using a larger rate, denoted by R prime. Therefore, especially when the rate is quite small, which is usually the case in lightweight crypto, these tweaks allow to reduce the number of required permutation calls to compute the digest, making thus the scheme more efficient. So now we are interested in the provable security guarantees of the sponge. And in order to argue that we have a good hash function, there are 3 classical security properties. The first one is called Primage resistance, where we are given an n-bit string H, and it should be hard to invert the hash function on this input. Then we have second Primage resistance, where additionally to H, we are provided a message that was used to complete this digest. And it should be hard to find a different message that hashes to the same value. And finally, there is collision resistance, where it should be hard to find 2 different messages that hash to the same value. So historically, these properties are considered as very important, but they are not strong enough for some applications. So consider the following Mac construction, where the tag is generated by computing the hash of the key concatenated with the message. So in the random oracle model, this construction is secure. But on the other side, consider the plain Merkle-Damgard construction based on an ideal compression function. Then this hash function is Primage, second Primage, and collision resistant. But on the other side, it is exposed to length extension attack, making thus this instantiation completely unsecure in this Mac construction. So these classical security requirements do not capture all of the applications of the hash function that we would like to have. In fact, the best thing we could ever have for a hash function is a random oracle. But a random oracle is described by an infinite amount of entropy, while a hash function is described by a finite string of bits. So it's impossible to have one in practice. But there exists a security notion which captures this idea of behaving like a random oracle, and this is indifferentiability. So indifferentiability is a distinguishing game where the adversary is either in the real world or in the simulated world. In the real world, it has access to a primitive P that we assume to be ideal, so sample uniformly at random. And it has also access to the hash construction using this primitive. In the simulated world, the hash construction is replaced by a random oracle and the primitive by a simulator. The goal of the simulator is to mimic the primitive's behavior according to the random oracle response. In other words, it must maintain construction primitive consistency. And the goal is to show that the adversary can distinguish between these 2 words only with a negligible probability or with a number of queries which is unreachable in practice. So indifferentiability is much stronger than the previous security properties. It has been shown that indifferentiability implies security guarantees regarding any generic attack on the hash construction. So in particular, it implies Primage, second Primage, and collision security. Now, going back to the sponge construction, it has been proven to be indifferentiable with a bound of form Q over 2 to the C over 2, where Q denotes the number of queries. In fact, for the plain sponge construction, the bound is slightly better because this is the square of it. But in both cases, it tells us that in order to be able to differentiate the sponge from a random oracle with a non-negligible probability, one needs at least 2 to the C/2 queries. And below this number of queries, any attack on the sponge cannot be easier than the same attack on a random oracle. So this is what we can see on this table. For the classical security properties, the security bound is the sum of two terms. The first one comes from indifferentiability, while the second one is the success probability of a generic attack on a random oracle. So now we want to compare the security bound against the best known attack and see if the two quantities match. So for the classical security properties, the best attack cost is the minimum between two terms, and it corresponds to two different strategies. The first one is an attack that exploits the inner working of the sponge, while the second one is just a generic attack. So now for indifferentiability, collision, and second Primage, this is clear that the security bound matches the best known attack. However, for Primage, on one side, the security bound is exactly the same as the one of second Primage. But on the other side, in the best attack cost, there is an extra term in the non-generic parts. Therefore, when this term is larger than 2 to the C/2, there is therefore a gap between the security bound and the best known attack. And the goal of this work is to fill in this gap by proving a better security bound for Primage resistance, and it shows in particular the optimality of the best known attack. So now I will show the best known attack on the three classical security properties. And note that for indifferentiability, the best known attack is essentially the same one as the collision attack. So for collision attack, the idea is to exploit collisions in the inner parts within the sponge states. So to do that, we consider 2 to the C/2 different message M1 here. For each of them, we add them to the outer part of the IV. We apply the permutation, and it gives us 2 to the C/2 states, and we are going to store them in a list. Now, with high probability, there exist two different elements in this list that display a collision on the inner part. Now we can transform this partial collision into a full state collision by compensating the difference in the outer part using the second absorb call. So now we have two different sequences of message blocks that go to the same state. So in particular, it gives a collision in the hash digest. And this attack is expected to cost around 2 to the C/2 queries. Now, for the second Primage attack, the idea is also to exploit collision, inner collision in the sponge states. So we are provided here a first Primage. So in particular, we are able to compute intermediate states within the sponge when computing the digest. There is one state which is particularly interesting for us. This is the state right before the squeezing state. Let's call it Y. In particular, if we can reach this state from the IV using a different sequence of message block, then in particular, we found a second Primage. And to do that, we are again considered to use collisions in the inner part of the sponge. So this time we start from the IV, consider 2 to the C/2 different message, apply the permutation, and store the states in a list. Then start from Y, compute inverse absorb call, and check for collisions against the list, and compensate use the second absorb call to obtain a full state collision. And this attack is also expected to cost around 2 to the C/2 queries. Now, for first Primage attack, the situation is a bit more complicated because here we are not provided any intermediate states. And the idea of this attack is to first find a good state and then apply the second Primage attack. By good state, I mean that we need to find the state Y here such that the L consecutive permutation evaluation gives the state such that each of them have the desired outer part. So Z1 to the L. To do that, the best strategy is to start from a state during the first squeezing phase, Y1, with outer part Z1, and then cross our fingers so that the L-1 consecutive permutation evaluation gives us states with desired outer parts. So we require on average 2 to the N-R prime queries before finding such a state. And once again, once this state is found, we just apply the second Primage attack so that the total attack cost is the sum of the two terms. Now, adding the generic term on top of that, we obtain a best known first Primage attack which succeeds after around this number of queries. On the other side, remember that the indifferentiability bound guaranteed Primage security up to this number of queries. So in particular, the cost of the extra step that I described a slide ago does not appear in the indifferentiability bound. Therefore, when the cost of this step is larger than the cost of finding inner collision, there is therefore a gap between the security bound and the best known attack. This happens for schemes that have quite small primitives with small rates, which is usually the case of lightweight crypto schemes. And the contribution here was to prove Primage resistance with a better bond, so the following bond. And it shows it is a tight bond, and it shows in particular the optimality of this attack. In fact, this bond was already believed to be true. The designer of the Spongeon and Photon made security claims based on this bond, but there was beforehand no proof for that. So more concretely, so here we plotted the adversarial advantage according to the logarithm of number of queries for two different parameter sets that corresponds to two different schemes, so ASCON and Spongeon largest mode. So for ASCON, the state-of-the-art bond guaranteed primage security up to 128 bits. And the new bond levels security up to 192 bits. And in particular, the graph almost overlaps with the graph of the state-of-the-art attack, and the difference is only due to constant factors. Now for Spongeons, the state-of-the-art bond is almost is the same one as ASCON, so 128 bits. And in this case, our bond improves even more because it gives primage security up to 240 bits. In fact, ASCON and Spongeon both have the same capacity and the same digest size. The difference is in the size of the primitive. So the one of Spongeon is a bit smaller than the one of ASCON, and therefore the rate is smaller. And that's the place where our bond improves the most. So this is the place where the exact place where the bond starts to improve the state of the art. And in both cases, it happens at small adversarial advantage, 10 to the minus 36 for ASCON and 10 to the minus 64 for Spongeons. Now for the proof ID closely follows the ID behind the first primage attack. So remember that here we are in the ideal primitive model. So we assume that the permutation is random. Suppose that the adversary has found a primage. Then in particular, it must have found a cascade of L-1 permutation evaluation, giving the outer part Z2 up to the L. However, having such a cascade is not enough because it must be reached from the initial state. Now have a look at the state right before the squeezing phase, call it X1, and let Y1 be the image of X1 by the permutation. So it gives us a query, and depending on the direction of this query, there are two different scenarios. If the query was made in the forward direction, then the cascade is extended by 1. So now we require L good permutation evaluations. On the other side, if the query was made in the inverse direction, additionally to this cascade, then we require that an inner collision must have been formed during the absorption phase. So by doing this, we reduce the probability computation of finding a primage into the one of 3 smaller events. So now it remains to a bond each of these terms. So in the case where the query was made in the forward direction, then this reduces to a guessing game. In order to win, the adversary must have found a good X1. It is good in the sense that it gives access to a chain of L values, such that each of these values have the desired outer part. So in the proof, we have to argue that the other permutation evaluations of the adversary do not bias it towards certain values of X1. And after a few extra steps, we obtain a bond of form Q over 2 to the n. On the other side, if the query was made in the inverse direction, then the cascade part is a bit more involved, since in this case, we do not specify how does the adversary reaches the cascade. So for example, it can just start from a state with the outer part Z2, then make forward queries to reach DR, and then finish with inverse queries to reach Y1 and then X1. So in particular, the winning queries can appear anywhere in the cascade and in any direction. So here, since the cascade size is reduced by 1, we obtain a bond of form Q over 2 to the n minus R prime. Then the inner collision part is a classical result, so that we have the following upper bound. Here we have this extra term Q over 2 to the C prime prime, because remember that the first capacity is smaller than the absorbing capacity. And by gluing all of this term together, we obtain the primage.
All right, thank you for the talk. So do we have any questions? Feel free to come forward. Also on Zoom. So we have plenty of time. So otherwise, maybe one question. So do you know of other properties that are, so other properties beyond primage resistance where the indifferentiability bound is not tight and where we would like to have a better proof?
No, I don't know such property. In the case of the sponge construction.
In the case of the sponge construction, yeah. So I don't know, multi-collisions or something like that. Do we, you know, if there's a gap? Okay. Yeah, I think there's a question.
Hi, thanks for the talk. Sorry if this is kind of a basic question, but I noticed that you're proving indifferentiability in some kind of like ideal permutation model. So I just want to ask, do you know, are there any attacks on these constructions that might try to attack the permutation, and like how are those attacks?
You mean attack that that exploits properties of the underlying permutations?
Yeah. Oh. Oh, thanks.
All right. And again, maybe another thing. So for SHA-3, it doesn't matter, right? So in that case, the bound was already tight,
Yes,
right?
Because the SHA-3 outputs digest in one round. So
well, oh yeah.
but output does not improve the state of
It
the
doesn't
art
matter.
in this case. Yes.
Yeah. Okay. All right. All right. So let's thank Charlotte again. All right, so we're a bit ahead of schedule. I think we will go ahead, but then if you're too fast, we will take a short break after you talk to match up with the. Okay. Yeah. All right, so the next talk is block cipher based tree hashing by Aldo Gunsing, and Aldo is going to give the talk.
Thank you for the introduction. So like the previous talk, my talk will also be about hash functions. So we'll repeat a bit of the definitions, but I will go over them briefly. So a hash function is a function that maps an input of arbitrary length to a fixed length output. And as we saw, there are multiple possible security notions for them. So one example was the notion of collision resistance, which means that it should be difficult to find two different inputs that get mapped to the same output. But for some cryptographic schemes, this is not strong enough, and there are also other notions required. And the strongest one is that a hash function should behave like a random oracle, so that every output should be uniformly randomly generated and also independent from each other. Also, as we saw before, this is formalized as indifferentiability by Maurer et al., and also specified for hashing by Colon et al. And the second kind of construction we'll look at are Mac functions, but we will mostly use them to show that some hash functions are not indifferentiable. So a Mac function, like a hash function, takes an input of arbitrary length and maps it to a fixed length output. But this is a keyed function, so it also takes a key as an input. And they are used to check the integrity of a message. So when you send a message and you append a Mac to it, then that means that the message should not be able to be changed. And for this presentation, just two properties are important. So the first one is that it should behave like an integrity check. So if we know a message M1 and the corresponding tag H1, then it should be difficult to forge the message. So to find another message M2 with the corresponding tag H1. And the second property is that if you have an indifferentiable hash function, H, then the Mac function that uses this hash function and simply passes the key and the message to the hash function, then this should be a secure Mac. And there should be two possible attacks. So the first is exhaustive key search, which gives a security level of K. And the second one is that you could also find collision. So that's where we get the N/2. And we will mostly use this when we instantiate a hash function, then we will see that this function may not be a good Mac. And that will also mean that the hash function is not indifferentiable. So the classic hash construction is the Mercury-Damkaart construction, which is on a fixed size compression function f, and it simply compresses a message sequentially in blocks. So we start with an IV, and then we call the compression function with M1 as the key input, and then pass it through and compressed again with M2 all the way up to MM, and then output of the final compression call will be the hash output. However, this construct is susceptible to the attack. So suppose that we use it as a Mac function as before, so that we prevent the key to the message. And when we look at the outputs of M1 and M1 concatenated with M2, we will get these two constructions. So for the first box K and then M1, and for the second one the same, but with also M2 appended. And if we look at the Mac security, what we are looking at is that suppose that M1 is sent with a tag. So suppose we know M1 and the tag H1, and then we will look also given M2, can we compute this new tag H2 without needing to know the secret key K? And in this case, what we can see is that actually the first construction is repeated here, and that the intermediate chaining value will be equal to H1. So we can simply compute H2 by calling the compression function on H1 with the key M2. And because we do not need to know the secret key K for this is a problem. And this means that this is not a secure Mac function. And as a consequence, the hash function is not indifferentiable. So most straightforward way, I think, to fix this is to use domain separation. So now instead of having the message blocks as directly as key inputs, we will also append a bit to it, do the note whether it's the final node or not. So we will almost always append a 0, but only for the final block we will append a 1. And now the attack doesn't work anymore because this first construction is not repeated here because here we have a 1 and here we have a 0, so it doesn't work. And this construction is also shown to be indifferentiable by Coron et al. When it is based on an ideal compression function f. And this is more commonly done, is that often the hash constructions are based on a smaller fixed size compression function f. However, such an ideal compression function, we cannot build that directly, and we have to use another primitive. And a possible building block is to use a block cipher E. And the common way to transform a block cipher to a compression function is by using the Davies-Meyer construction, which uses a feed-forward in the data input. However, this construction is not indifferentiable from an ideal compression function. So we cannot compose these results, and not really the right abstraction level. So we really need dedicated analysis using the block cipher as the underlying assumption and not the compression function. And this was done by Damenen et al., where they try to find sufficient conditions for hashing modes based on the block cipher and also some other constructions. However, it turned out that there was a flaw in the paper, as Samuel Neves found that it also proves faulty constructions secure. So now we have the same construction as before with the domain separation, but instead of using a compression function f, we will use a block cipher. And now it is insecure again, because we can make use of the fact that the block cipher is invertible. So suppose again that we know the message M1 and the tag H1, and we will try to forge it to any new message. And what we can simply do is compute the intermediate chaining value CV by calling the inverse block cipher, and then going forward again with a different message as a key input. We do not need to know the secret key K for this, but we can still compute this H2. So this shows that the paper proves some faulty construction secure, so there's problem there. And in errata, I and also with Damen and Manning did provide a quick fix where we require additional truncation in the conditions to fix those. But there's also an error in the proof, and if we look more closely at what the error is, it's actually more fundamental about the indifferentiability setting. So now we'll quickly over the indifferentiability setting. So it is a bit technical, but it is necessary to explain what the error is. So indifferentiability setting, it is a distinguishing game. So we have a distinguisher D, and it tries to distinguish between the real and the ideal world. And it can make two kinds of queries, or yes, but one kind also has two kinds. But it can make primitive and construction queries. So in the real world, the primitive is the block cipher, and the construction is simply the construction. So how does the construction compute an output? Well, it simply calls the block cipher to get the output. And in the ideal world, what we want is that the construction behaves like a random oracle. So we put a random oracle there, but a random oracle doesn't really have a primitive. So we define a simulator for the primitive. And what simulator will simply do is basically always give random outputs, but it also has to behave like the primitive of the construction. So when it finishes like the computation of a message, then it has to be consistent with the random oracle. So in those cases, it will query the random oracle, and then it's basically forced to take some value. And because we use the block cipher as the underlying primitive, we can also make forward and backward queries for this primitive. So now we can take a look at what the flawed reasoning is. So it will, the reasoning takes multiple steps, and some are also fine. So it starts with modifying the distinguisher D to an equivalent one D prime, and this step will actually be fine. So what does our D prime do? So it starts with just interacting like D does. So on the right side, I have an example, and this is actually the attack we had earlier. So what the attack did is that it started at the end, it made an inverse query and then forward again. So if you look at it more formally, it starts with a construction query to get the first tag H1. Then it made an inverse query on this H1 with our message to get a supposed chaining value CV prime. And then it made a forward query again on this supposed chaining value with a different message to get, well, a supposed new tag. And then we call the construction oracle again to check whether these correspond or not. So after interacting like D, what D prime additionally does is that it adds verification queries for these construction queries. So we called construction oracle on K appended with M1 and K with M2. And we will also verify these queries. So then it first calls the primitive with the IV with the key as input to get chaining value, and then with this chaining value with M1 to get H1, and the same for H2. And they have a bit of overlap, so one query is repeated, but we don't denote it. So after these verification queries, D prime will simply output the same decision as D did. So in this case, it checks whether these two values are the same, but it's not that important. And what we now can see is that these verification queries and these construction queries contain duplicate information, because here we have an H1 and in the primitive queries as well, and it's the same for H2. And the primitive queries they also contain the chaining value, so they contain more information. But the construction queries, their outputs can be derived from primitive queries. So how the reason goes is, well, then we can simply ignore them to make the analysis easier. But this cannot be done. This is a problem because it ignores that the output of the construction queries can have an influence on the later queries. So what we had is that the output of the first construction query was H1, and we actually use that value in our first inverse primitive query. And if we ignore the query, well, H1 is not there, so this does not work. And we can also not like fake some value that's randomly generated, because the verification query should output the same H1. But we don't have it, so it really is really a fundamental flaw that ignores a lot of the interaction between the construction and primitive oracles. And the same flaw is actually also present in many other indifferentiability papers. So there are 2 also on hashing and also 4 on the sum of permutations. And these are actually also all the works on the indifferentiability of the sum of permutations. So maybe I have a slight positive note is that this reasoning does hold in the sequential indifferentiability setting, where all the primitive queries have to be made before the construction ones. So what we can say is that these results are downgraded to this weaker setting, so that they still have some positive results. And if we look at the case for hashing, what we saw earlier, that the errata fix the conditions by requiring sufficient truncation, but this is not that great of a fix, as not really all modes can apply this. So in this work, look at also some other options. So the first one is truncation again, but there we also have some interesting variations. The second one is the enveloped finalization, which is a generalization of enveloped Merkle-Darmgaard. And the third one is feed-forward finalization. This is also one we'll look at in this presentation. So the feed-forward is a common finalization. And what it does is that it takes the input of a block cipher call and also XORs it with the output. And in this paper, we also have more assumptions on what the input looks like. So it consists of 2 parts. The first one will always be a chaining value of a previous compression call. And for the second one, we simply use an IV. And what we see is that this feed-forward is actually only required for the final compression call, while for indifferentiability, while all compression functions, it's only the final one is required. And I said like, oh, we have this IV2, but it's not necessarily a fixed value. It can also, to be more flexible, be allowed to have also multiple possible values. For example, a counter, which we will see later. But the simulator has to loop over all these possibilities in some cases and query the random oracle for everyone. And having many options does not really influence the advantage of the distinguisher D, but it does increase the query complexity of our simulator, which is a bit more subtle, but it's also something that should be limited. So a major application is Blake 3, which is a recent block cipher-based 3-hashing mode. And we will, for this talk, we will focus on the final compression call. So it looks like this. And what we see is that the key input is equal to the final message block M. And the data input consists of a chaining value. And for the other part, it contains an IV counter T the number of bytes be in the message and some flags. It's not all that important, but the counter T is more interesting, which we'll focus later on. And the output is actually split into the lower and the higher bits, and then there's some internal XOR, and then the chaining value is XORed with one of them. So it does not exactly follow the definition we had earlier, but for the proof, that's actually fine. It's because we only use that the chaining value is fed forward. So Blake 3 has two different modes. So one is a fixed output mode, and for this it uses truncation, which was studied before and is fine. But it also has an extendable output, and there it uses the counter. So to get multiple blocks of output, it starts with setting the counter to 0 and getting the output, and sets it to 1 and appends it, and so on. And as I said before, Blake 3 uses the feed-forward finalization. But what we said is that like this non-CV input, which we call IV2, should have a limited number of possibilities. But because of this counter, which just can go on and on, there are actually many possibilities. And this leads to an interesting property, namely, so let's assume that we know a message M and its like full message and its hash output at some offset T for the counter, but we do not know the counter itself. What we can actually see is that we can then compute this counter directly, while as ideal behavior, we would expect that we would have to try every possibility and make a query. So here, all the values that are known are highlighted. So the chaining value can be computed from the message, and the last message block is also part of that. And we assume that we know the full hash output, so also the HL and HH. And what you can see, if we start at the right, first there's an XOR with the chaining value, which is known, so we can move on, and then we have an internal one, which we also know, so we also get the VL and the VH are also known. And because we also know the key inputs, we can make an inverse query and compute all these inputs, including the counter T. So in short, if we know a message M and its hash output, but not the counter, then we can compute this counter. And as a consequence of this, we cannot really rely on the secrecy of this counter. And we can illustrate this by defining a contrived Mac function. So a Mac function had the key input and a message. And in this case, we assume that the key is 128 bits, and we will split it into two parts. So the first part of 70 bits and the second part of 58, just so that the definitions work out. And a bit like before, to compute the tag of the Mac, we will call the hash function on the message input with the key appended to it. But in this case, we move part of the key to the offset. And ideally, this would only allow for a key recovery attack into the power 128 bits. But it turns out we can actually do it in 2 to the power 70 queries. So for an attack, we assume that we know the message M and the hash output. And remember, if you know the message and the hash of that full message, then we know the counter. So these M's are actually not the same. So in this case, we know M, but K1 is also part of that input. So we do have to guess K1, which is where the 2 to the power 70 comes from. But once we know that, we can compute the counter T, which is equal to the second part of the key directly. So we don't have to guess that. So then this gives the desired result. So concluding, we saw that many previous indifferentiability proofs contain really a fundamental error. and these results are downgraded to the weaker sequential indifferentiability setting. And for block cipher-based tree hashing, we had an unsatisfactory fix that requires truncation. And in this work, we prove also other finalizations secure, including the common feed forward. And we also saw that Blake 3 can be proven indifferentiable, but it does require a public offset in the extendable output. So that is not ideal behavior, but in practice also not that big of a problem. So that's the end of my presentation. Thank you for your attention.
We still have a few minutes for questions. So does anyone have a question? Yeah, looks like it.
So I just wanted to ask, thanks, this is a cool talk. I wanted to ask if I kind of have an intuition for what security guarantees I'm getting with an indifferentiability proof on a hashing mode. I don't have a lot of intuition for what the sequential indifferentiability is telling me. Because that seems like it's very weak intuitively. So do you have a good way of a good guide for how should I think about the implications of just having sequential indifferentiability in the proof?
Yeah, so this is a much weaker notion, and I think it does have also more limited applications. But so I included it so that they still have positive results, but we really should want to have an indifferentiability proof and not a sequential indifferentiability one.
Like participation proof.
Yes.
So again, forgive me if this is a somewhat basic question, but as I learned in cryptography class, hash functions are not implied by one-way functions, which means they cannot be constructed out of PRF. So my question is, if you have an indistinguishability proof for a hash function construction from a block cipher, what additional assumptions are you making on the block cipher to make that possible? Because you couldn't just assume that is PRF.
I assume that it is an ideal cipher.
Okay.
But you get like indifferentiability, and that's also some. So like indifferentiability also not exactly random oracle, but in many cases it behaves like one.
Okay, so you have some kind of indifferentiability assumption on the block cipher itself.
Yes.
Okay, thank you.
Yeah, although thanks for a really interesting talk. I don't have a question, I have a complaint. This is actually not to you, it's to the community in general, right? As you point out in your paper, there's no proof that indifferential hash functions resist length extension attacks, but that was more or less the promise made of why we introduced the indifferentiability framework. But it seems in the past more than 10 years, there hasn't been much progress that I know of in this area.
But so I think an indifferentiable hash function does imply that it doesn't have the length extension problem. So it's more, I think the length extension is more that shows why you want an indifferentiable hash. So merk dan guide
on the spot, right? But okay, here. Although we expect them to, we do not have proof that current indifferential hash constructions resist length extension attacks.
Really?
This is in your paper.
Hmm?
I'm reading this in your paper.
Oh, really?
Is that just a statement about the limitations of
or maybe let's do this offline later.
Yeah.
There's a technical problem that's been pointed out at Eurocred 2011 related to this.
Okay.
Yeah. Like it's technical and it's related to multi-stage adversaries. So it's
yeah, so that's true. That's like the indifferentiability is only about a single stage and not multi-stage. So maybe that's.
But all of or perhaps I'm wrong about this. All of the formalizations of length extension attacks involve a multi-stage adversary. Or
yeah.
perhaps there's
think we'll
Okay,
look at
let's
it offline.
more
more.
time, so I just wanted to discuss it.
Yeah.
more. Like, maybe we want to take this offline
Yeah.
to discuss further. Anyway, thank you for a really interesting presentation.
Thank you.
So actually a quick clarification. So so since you found the bug in a series of papers, so are there still statements that remain open? So do you have examples of things that are where we only have sequential indifferentiability and we will need to fix things?
Yes, so this is interesting for the sum of permutations, because there what I first thought, and there's like, oh, it is more like a technical problem, and we can probably just fix it easily to make it also indifferentiable. But I also looked at it more, and it's still ongoing work. But surprisingly, there is actually a difference between the sequential and full indifferentiability. So the attack is like you have a specific simulator, so not that clear, but there really is a difference more than you maybe would expect.
See,
So it is not really non-trivial to move from sequential to full differentiability.
and by the way, when you say sequential, because both variants exist, do you mean construction before primitives or primitive before construction?
Primitive before construction.
Okay, yeah. All right. No more question. Let's thank Aldo again. Then the next speaker can sit. And we are back on schedule. Thanks for asking questions. All right, so the next talk is on provably secure reflection ciphers, and this is joint work by Tim Bene and Yulong Chen, and Yulong is going to do the talk.
Okay, so thank you, Stefano. Thank you for the introduction. This talk is not really about hash functions anymore, so we are going to talk a little bit about another primitive, namely block ciphers. Cryptographers has long been fascinated by the self-inverse or the semi-self-inverse property of encryption device. A famous example is the Enigma Rodo machine, where the encryption and the decryption operations are identical. This is enabled by the middle reflector, which makes the encryption device much more compact. Now, this self-inverse property can actually also be found back in the modern ciphers. For example, ciphers based on the famous FISO network. Example is the block cipher. Now, those FISO ciphers have the following property, namely decryption is always possible. That is equal to encryption using round keys in the reverse order. Then this property leads actually to the fact that we do not need to use our underlying round functions to be invertible anymore. And this gives us actually more flexibility when we need to use those round functions, because during decryption, we can also just evaluate those round functions forward. Another property is that not the entire input string is updated every round. We can see that's only the right part is evaluated round function. So the generic security of the FISO ciphers actually first started by Ruby and Strakov in 1995. Now, that said, another important class of ciphers are actually based on another design structure, which is the alternating cipher structure. And the famous AES block cipher is based on. Here, the authors were actually first inspired by Shannon's idea. And a very special property of the key alternating ciphers is that they usually requires less rounds than the FISO cipher. And another property is fast diffusion, since the entire input string is updated every round. Now, the limitation about the key alternating ciphers is that they do not have the self-inverse property like FISO ciphers. And the generic security of the alternating ciphers was first studied by Etd Transform in 1991 for the single round case, and by Bogdanov et al. 2012 for the multiple round case. Now, I explained about both type of design structures. Both design structures have their own advantage and limitations. You may wonder, you will get the following question, whether we can combine the two ideas such that we can get a design structure such that it's similar to the key alternating cipher design structure, such as best rounds are needed to build a secure cipher while still obtaining the self-inverse property of the FISO network. The answer to this question is actually already given in 2012 by Bogdanov et al., where they introduced the Prince block cipher. So here you can see on the slide this design property, the design structure of the internal structure of the Prince block cipher, and we call it the key alternating reflection cipher, where this R is actually a reflector, is normally an solution. And this type of ciphers has following property, namely reflection property that decryption is always equal to encryption using related keys. And this makes the cipher particularly suitable for low latency, low error use case. However, unlike the case for FISO or for key alternating ciphers, the generic security, the study of generic security actually missing till this moment. So in this work, we are going to study the generic security of the reflection. Before I'm going to do that, I first want to explain what's generic security for block ciphers. In order to do that, we need to define an attack. So at the beginning of the game, so one of the two worlds are chosen, either the real world on the left side and the ideal right side. So this attacker here can make Q queries to the construction oracle, which is the proposed block cipher in the real world ideal uniform permutation in the ideal. And at the same time, that attacker can also make P primitive queries to the underlying primitives are the permutations which block cipher is built on, since we are dealing with ideal permutation model. So after A's communication, A should state which of those two worlds was interacting. And the probability of that attacker can distinguish the two worlds, actually, that's actually the security is actually measured by this probability. And for the rest of this presentation, we are going to denote this probability by this Primage function. And we can see that the more query access that the attacker gets, the higher the probability that it can distinguish from the two worlds. Hence, this advantage is actually a function of the construction and the primitive queries. Now, we can only say that the cipher is secure if this function is negligible. Okay. So we are going to focus on the two rounds case here, and we try to minimize the number of randomness that's are needed. So then you first want to go to the 1C case, but this construction is obviously insecure when the vector is linear. Since then we can just choose message M to obtain the corresponding ciphertext, and we can choose another message that's equal to this ciphertext, and then to obtain C, and then we can see this new ciphertext actually equal to the previous message once vector is linear. Then of course we can immediately distinguish the real world from random. We can also second and the fourth key sigma of K versus linear inclusion, but the problem here is that different construction is in that case not even secure up to the birthday bounds when sigma is linear. Since the reason here for is because this file with K XOR sigma K is actually not uniformly random. So we show that our work that's because for linear involution, they have too many fixed points, and so we'll get problem with zero site attack, which I'm going to explain in one of the slides. Now, therefore, we are going to focus on constructions to independent keys. And we do not claim that one key case is not possible, since we do believe that if we want to use a single key, then either it's need to have a special choice of the middle reflector R, or we need to use non-linear reflector sigma that has less points, but then this can give a difficult situation when we need to bound the bad events in the security. So this will be left us one of two. Now, in this work, our first contribution is to prove the generic result of the two-round alternating friction cipher case, based on the assumption that linear reflector is and two alternating bonds. And this is our security bond obtained here. And the construction has the following property that decryption is encryption using the two keys, as two button keys. And I'm going to say a little bit more about those two terms in the bonds and why those terms are tied for the general choice of the first one is actually the PQ term. Then this is actually just an information theoretic hack. So here we need to choose two Q construction queries and P primitive queries. That's P squared Q is 2 to the power 2n. And then for each possible pairs K1 and K2, we need to find a pair of primitive queries such that this those equations, that's mxo K1 is equal to first primitive query U, and XOR K2 is equal to second primitive query. So once this happens, then we can check whether this this internal relation holds relation. So once those all holds, then we can break the system. But as mentioned, this is just an information theoretic hack. So reason is that the attack is 2 to the power 2n table lookups. Then therefore it's really impractical. But it gives the idea that this PQ term is actually unavoidable in bonds. But the next attack is actually more interesting, since practical attack that can be performed in real time. This is actually a variant of the mirror slide attack of Dongelman, Keller, and Chamy in Eurocrypt 2012. So the idea here is actually, we can perform this attack if this middle reflector has many fixed points. And in order to do that, we just need to use 2 to the power n over 2 distinct messages, different ciphertexts. Then the high-level idea of the attack is that we need to find a pair of construction queries that satisfy this equation. So we need to find the M that's XOR with new message and this new ciphertext that's equal to the XOR of the two keys. But then at the same time that this XOR of keys is equal to the XOR of new message with ciphertext. Means that here the value here needs to provide with this value, and value here needs to provide value. So once this can bounce, then we are able to recover the value of K1 and K2. And this is really a practical attack that can be performed when we have enough fixed points. So we actually can. So there is a chance that we may be able to improve the security of the construction when we choose a reflector with not so many fixed points. Then there's maybe a chance that we can avoid this attack and avoid this Q squared term. But this seems also one of the fields. Now a little bit idea about the security analysis is performed using Batalan's linear theory, where the formulas are given here. I'm not going to explain details, but we have two terms. The green one is actually the probability of the bad transcript, while this blue one is actually obtained by the ratio of the good transcript in real world and ideal world. And here we obtain this blue term by variance of ideal first iteration of near theory. What that is, you can check the details of it. And we are dealing with ideal permutation model here, and here attacker will have internal access of the underlying current type. And since we have a single permutation case, we do need to have domain separation in order to prove security. This is actually guaranteed by by introducing a bad event that's similar to that's one zero side attack, Q square term. So I'm not going to much into details about the security analysis. So this is our first contribution. Our second contribution is a Keyland Standard. So I first want to explain the old Keyland Standard introduced in the Prince and Bounty cipher. They use the FX structure which is showed here, which they use the external K to extend the Keyland from 64 bits to 128. Now they proved their results using the fact that so star is actually an ideal reflection cipher, and we can see that the looks like things like this sides star, and they proved the security of Prince Keyland Standard to this bond. We can see that's a typical birthday type of term, which can sometimes be insufficient for some application. And therefore, the authors also use the version 2 of Prince block cipher, which uses alternating round key, and where the middle reflector is also modified for a little bit. Now, our second contribution is we introduced this new Prince, the new Prince Keyland extender, which has following security bonds, and our proof is based on the assumption of ideal cipher, and our results is actually a direct deduction from the one of security result of two round key alternating ciphers. But in order to use the security result of key alternating ciphers, we first need to improve the security bonds of two round key alternating ciphers. See that from this graph here. This is actually the bond that's obtained from the result of crypto 2014. Well, this is our security bond. And we did that by improving the stone capture lemma using variants of software quality. And this is actually gives us an improved security term in bad events, which leads to better security bonds. We still want to mention that what we proved here is actually that Piv Construction is generically or secure against generic attack up to this term. However, in order to use this construction for practical applications, then we still need concrete script analysis, and in order to make sure there will be a dedicated attack. So if we compare our construction with the original FX design, then we can see that that's actually the only difference that we have by exploring K and before and after the vector, while we obtain a much better security bond than the original bond, which allows us to make more construction and primitive queries. And if we compare our construction to the Prince version 2, then we can see that while our construction just have a change from the original Prince block cipher, and the Prince version 2 actually use two alternating keys, and besides their reflector is modified in that way, it doesn't really preserve all the reflection properties. So we can see that our construction actually compares in favor. And the last slide conclusion. So our new result is first generic treatment of reflection ciphers, where we have two main contributions. The first one is we prove the your result for two rounds key alternating reflection cipher, and we also provide a new Keyland standard with better security. And for future research topics, yeah, there are many things that can be done. For example, if we, as mentioned before, we can have a look at the single key case with whether we can try to modify the middle vector to have this key case. And yeah, whether we can also modify the middle vector such that maybe this Q square term can be avoided. Or if we can look at the general case, like for the key alternating ciphers, we go to the mutable bonds, whether we can get better tight security bonds. And if we can extend this idea to of the reflection ciphers to the triple reflection cipher. So yeah, this was the work done during my PhD. Now a small commercial for myself. Yeah, so thank you for your attention. And yeah, so that's.
All right, thank you. Thank you for the talk. Are there any questions? Or... So just a quick one. Then so what do you expect the biggest difficulty to be to increase the number of rounds? So is it like new sum capture theorems, or is it just?
Yeah, definitely, because as I mentioned, the one with the single key case, because yeah, maybe I back why. Because I think that I mentioned before that function of k XOR and sigma of k. So yeah, that's actually the case where you don't get that's not uniform. And go back. Yeah, this one. Yeah. So this thing is actually not uniform if the sigma is linear evolution. So if we can use a nonlinear evolution, then we can choose one that probably have a better density. But the problem is here, indeed, you will get problem with some capture lemma. Then we need to bond the bad events. Then we usually need to have that this thing should be linear in order to use those tricks. But in the case of nonlinear case, then we cannot use that trick. And probably some capture lemma cannot. Then we need to have a, yeah, I would say, a better or a difficult technique to bounce the bad event. That's one of the difficult cases. Also for the mutable round case, I think it would be more difficult than the case of key alternating ciphers. Now we only have so wow, we have one permutation here. Well, if we extend it to a mutable round, we will have mutable permutations, but each permutation is used twice. So the forward and the inverse. So that's what I
All right, thank you. So if there are no more questions, then let's thank Yilong again. All right. So this takes us to the last talk of the morning. That is about overloading the nonce, RAG PRPs, Nonset AAD, and order resilient channels. That's work by Jean-Paul de Gabriele and Vukazin Karadzic.
Thank you.
Jean-Paul will give the talk.
So this is joint work with my student Vukashin, who unfortunately couldn't be here. So in this work, we make contributions in three main directions. We introduce a new notion for pseudorandom permutations called rugged PRPs. We introduce a new variant of AAD called Nonset AAD. And we show how these can be used to construct order resilient secure channels. And the main part of our title refers to an underlying theme in our work, which is that of overloading the use of the nonce. Traditionally, the nonce serves to diversify ciphertext, but in this work, we use it also additionally to provide authentication and to recover the correct ordering of the messages in orders between channels. So I'll start this talk with presenting the definition of rugged PRPs. I'll describe then a construction for realizing rugged PRPs called the UIV construction. And then we'll see how we can transform rugged PRPs into AAD schemes with a variety of security properties. We'll then introduce Nonset AAD and see how this can be used to construct orders between channels. Okay, so let's start with the definition. The syntax of a rugged PRP is essentially a variable length tweakable cipher over a split domain. And that means that the inputs and outputs of the tweakable cipher will consist of pairs of strings, which we refer to as the left string and the right string. And in this presentation, the left string will consist of a string of n, size n, where n is typically 1 to 8 bits or 256 bits. And the right string will be of variable length. So then a tweakable cipher consists of two algorithms, enciphering and deciphering. Enciphering here will take a tweak and a pair of inputs XL and XR and return a pair of outputs YL and YR. And for every tweak value, this algorithm will define a distinct permutation. And then the deciphering algorithm simply inverts this mapping. In terms of security, rugged PRPs achieve or strike a level of security that sits right in between that of PRPs and strong PRPs. And at a high level, this is achieved by giving the adversary full access to the enciphering algorithm, but only giving it partial access to the deciphering algorithm. So in contrast to the strong SPRP notion, for example, where the adversary has full access to both, and PRP, where the adversary has only access to the enciphering algorithm. Okay, so here's the definition in more detail. We give the adversary oracle access to the enciphering algorithm and deciphering algorithm. But now we impose two main restrictions on what the adversary can query to the deciphering oracle. The first restriction is that it cannot make a deciphering query using a left value that was previously returned by the enciphering oracle. And this holds no matter what the other values of T and YR are. And the second restriction is that the adversary cannot repeat values of YL across different deciphering queries. So note that these are rather limiting restrictions that we make on the adversary's queries, and are not just there to avoid trivial win conditions. These are much stricter. So then, to relax a bit this notion, we introduce a second way that the adversary can interact with the deciphering algorithm, and this is via a guess oracle. And the guess oracle takes all the inputs, takes as input all the inputs required to the deciphering algorithm, plus an additional input XL prime, which serves as a guess of the output of the left value of the deciphering algorithm. And the oracle returns true or false, indicating whether this guess was correct or not. So that's the real world. Then when we change, so to recap, deciphering can be accessed by the adversary in two separate ways. We have the deciphering oracle on the one hand, which has restricted queries but returns the full output. And then we have the guess oracle, which has unrestricted queries but returns only a single bit of information. And these gives two ways of interacting with the deciphering algorithm. Then that's the real world. So in the ideal world, we simply change the tweakable cipher construction to an ideal cipher one. And now for an ideal cipher pi, we note that the adversary can only make a successful guess query with negligible probability. So we simplify the definition a bit further by replacing this guess oracle with a dummy oracle that always returns false, no matter what the input is. And in order to make this change now, we have to impose some mild restrictions on what can be queried to the guess oracle, but these are just there to avoid trivial win conditions and don't significantly weaken the notion. So that's the formal definition. A few notes about the definition. So the term rugged is meant to reflect the intermediate overall security of the primitive, but more importantly, the asymmetry between the security that is required from the enciphering algorithm and the deciphering algorithm. So the enciphering algorithm is now required to be more pseudo-random than the deciphering algorithm. And the second point to note is that this notion is mainly intended for variable length ciphers in the context of the encoded and cipher paradigm. Essentially meaning that we're thinking of variable length tweakable ciphers from which we can easily realize AAD schemes with a variety of security properties. And is not very meaningful in the context, for example, of tweakable block ciphers, right? And the definition itself might seem a bit artificial, but it is motivated by the encoded and cipher paradigm and certain features that are common to various constructions of variable length ciphers. So with these in mind, then the definition is a rather natural one. So let's see now how we can construct rugged PRPs. Our starting point here is the PIV construction, or protected IV construction by Shrimter and Terashima. And this construction builds a tweakable cipher construction that achieves the stronger notion of SPRP security. It consists of 3 layers. So the first layer and the third layer consist of a fixed input length tweakable cipher with a variable length tweak size. And the middle layer consists simply of a variable output length PRF that is typically instantiated with a sum block cipher in counter mode. And then our construction, which we call the unilaterally protected IV, is simply obtained from this construction by dropping the last round. And this construction was already considered by Shrimter and Terashima, but it was shown to be not sufficient for SPRP security, and hence it was dismissed. But here we show that it's enough for achieving RPRP security. So it automatically gives a separation showing that RPRPs are strictly weaker than SPRPs. Another nice feature of this construction is that it can be instantiated from GCM components, leading to a performance characteristic that is very similar to GCM SIV. And it is closely related to 2 other constructions, and one is called MiniCTR by Minamatsu, and the other one is called GCM Wrap by Ashur, Dunkelman, and Luix from Crypto 2017. And I'll highlight as we go along how this relates to these other 2 constructions. Okay, so let's see now how I can transform rugged PRPs into AED. The problem of transforming a variable length cipher into an authenticated encryption scheme is a classic one that dates back to 2000 and was studied by Bellari and Drogaway, and was then revised in the work of Shrimter and Terashima. And however, both of these works require that the cipher satisfy the stronger notion of SPRP security. And in this work, we revisited this paradigm, but we'll make do with the weaker notion of rugged PRPs. So our first construction, our first construction is the Etd Transform. So to transform the cipher into an AED scheme, we encode the nonce and the header into the tweak. We place the message into the right part of the input, and we put some redundant bits into the left part of the input. In this case, shown as all zeros. And then decryption works by applying the deciphering algorithm in a natural way and checking whether the left output is equal to the all zero string. And if that's the case, the message is released as the output. Otherwise, decryption returns an error message. So in the paper, we defined it a bit more generally, but here we simplified it a bit for cleaner exposition. And our main result here, our first result, is that if the cipher is an RPRP secure cipher, then this construction not only yields a secure AED scheme, but also one that is secure against misuse, that is repeating nonces. However, the asymmetry in the rugged PRP definition prompts us to consider an alternative construction where we now use deciphering to encrypt and then ciphering to decrypt. And now, remember that the definition required, for example, that the left input to the ciphering algorithm never repeats. So this becomes a natural candidate for the nonce. And since we're using the left part for the nonce, then we have to place the redundant bits in the right part. And in this construction, because we're using ciphering to decrypt, it turns out to be okay and yields a secure construction, but would not have been okay in the previous construction. So then here, decryption proceeds in a similar way. We apply enciphering to decrypt, and we check that the redundant bits are equal to 0. And here the result is that, again, if the cipher is an RPRP, then this construction yields a nonce-hiding AAD scheme that is secure under the release of unverified plaintext, or RUPAE security. And when the tweakable cipher is instantiated with GCM UIV, this construction corresponds to the GCM wrap construction by ADL17. However, we can instantiate this construction a bit differently and obtain a scheme that yields a nonce-based scheme with more compact ciphertext. So essentially, we don't really need the extra redundant bits. We can simply use the nonce itself as the redundant bits. So we can get rid of the extra zeros that we're appending in the message part. And instead, during decryption, check that the provided nonce of the decryption algorithm is equal to the recovered nonce and prime. And this has a more compact ciphertext when compared to GCM wrap, for example. And again, we have a similar result here that if the underlying cipher is RPRP secure, then this yields an AAD scheme that is RUPAE secure. Okay, so let's now get into the new variant of AAD called Nonset AAD. And I'll start by motivating the primitive with a construction, and then I'll define later more formally what the primitive is. So essentially, the last trick we saw of using the nonce for authentication can also be applied in the first construction that we saw, the Etd construction. And this would indeed, when instantiated again with the UIV construction, this would yield something that's quite close to the MINUSCTR construction by Minamatsu. However, we can generalize this construction further and essentially replace this equality check between the nonces with a set membership test. So if this, instead of checking for equality, we check that the recovered nonce and prime is within some set W of nonces. And if this says, if the size of the set is limited, then this construction would still give us adequate integrity. And this construction is what we call the AWN for authenticate with nonce transform. However, it does not yield a standard AAD scheme. It yields something that we call Nonset AAD. And again, here we have this analogous result that when the underlying cipher is RPSP secure, this yields a Nonset AAD scheme that is misuse resistant. But let's now define more formally what a Nonset AAD scheme is. So syntactically, the main change is in the decryption algorithm, which now takes, instead of a single nonce, takes a set of nonces W and returns a pair of strings, n prime and then prime, if decryption succeeds, or if decryption fails, it returns a set of error messages. And it is required that whenever decryption succeeds, the returned nonce and prime is included in the set W. So at a high level here, what's happening is that the set of nonces indicates to the decryption algorithm which ciphertext can be accepted at this point in time, right? And in return, the decryption algorithm returns a nonce indicating which of these nonces in the set was associated successfully to that ciphertext. Then we need to adapt correctness as follows. So correctness now guarantees that whenever this nonset includes the nonce that was used to produce the ciphertext, decryption must recover the original message and the original nonce. And in terms of security, security can be translated in a straightforward manner. We only need to adapt the prohibited queries that the adversary is prohibited from making. So essentially, the adversary cannot make queries of the following form for a ciphertext C and a nonset W, where W contains the nonce that was used to produce that ciphertext using the encryption oracle. Okay, so why is this primitive interesting? It is a natural primitive to consider in the context of order resilient channels, such as QUIC and datagram TLS, which employ window mechanisms. And we'll see that Nonset AAD serves as a stepping stone from which a variety of secure channels can be easily realized. Alternatively, there's another construction of how to construct Nonset AAD. It can be realized in a black box manner using, or in a generic way, using nonce-hiding AAD via straightforward generic transform. However, the construction we've seen, the AWN construction, has the advantage that it yields more compact ciphertext than this generic transform using nonce-hiding AAD. Okay, so let's see now how this has applications to order resilient channels. So by order resilient channels, we mean protocols like Quick and TLS that try to realize secure channels over unreliable transports like UDP. And in particular, because of that, they need to be able to handle ciphertexts that are delivered out of order. And in general, with constructing such channels, there are several possibilities for how to handle reorderings, replace, modifications, and deletions of ciphertext, and how much of each can be tolerated. And typical constructions employ one or more window mechanisms, which typically add to the complexity of the channel description, which makes them hard to analyze and understand. In general, it is often unclear whether these additional mechanisms, how they interact with the AAD scheme, and what is the resulting overall security of the channel. So we said that there are a number of choices that one can make on the functionality of such a channel. And mathematically, these are normally formalized via something called a support predicate. And the support predicate takes three inputs. It takes a ciphertext, a list of the ciphertexts that were sent until this point, and a list of the ciphertexts that have been received and whether they have been accepted or rejected. The support predicate determines whether this ciphertext should be accepted or not. And the support predicate was developed in the works of Buckendall 19 and Fischling, Gunther, and Janssen 20 as a generalization of the silencing approach by Rogaway and Jung from 2018. And the support predicate permeates all aspects of the secure channel, from correctness to security to the notion of robustness that was put forward by FGJ20. So our main contribution here is the following generic transform for building a order resilient channel from any Nonset AAD. And this construction is generic and universal in the sense that we can construct a channel with any desired function that we require. So essentially for any desired support predicate. So it consists of two main components. The first one is the Nonset AAD, and whose components are shown in blue. And the second building block is what we call a Nonset processing scheme, whose components, the components of which are shown in red. So this consists of a tuple of 4 algorithms. The first one is simply a state initialization algorithm. Then we have a nonce extract algorithm in the send from the sender side, which takes the sender state and returns an updated state together with a nonce that is then fed to the encryption oracle. And at the receiver side, we have a nonset policy that, given the current state, extracts a set of nonces that are then fed to the decryption algorithm. And if the decryption succeeds, then we call the state update algorithm, it's called, on the nonce that is returned by the decryption algorithm and the current state. And this updates the state and also returns a message number indicating the position of the recovered message within the current sequence of messages at the receiver. So we prove that this generic construction is correct, robust, and secure in a generic way for any support predicate that one defines. And what we require is that the Nonset AAD scheme is secure and that the Nonset processing scheme satisfy a functionality property that we call faithfulness. So at a high level, the support predicate is oblivious of the representation that we use for the ciphertext in its inputs. So in particular, we can use the nonces to identify the ciphertext in the inputs to the support predicate. And essentially, the faithfulness requirement says that the Nonset processing scheme faithfully reproduces the support predicate logic over the nonsense. So it's merely a functionality requirement, and it's not a security requirement. And the nice property of this construction then is that the protocol designer can simply tune the nonset processing algorithms to obtain the desired functionality and plug in their favorite nonset AAD scheme, and correctness, security, and robustness will be automatically guaranteed. So to conclude, we've introduced a new notion of rugged PRPs that strikes a new trade-off between security and performance. And in particular, we have used it to show that the encoder and cipher paradigm can be made to work with weaker notions than strong PRPs. And with this abstraction, we were also able to provide a systematic exploration of the different AAD schemes and nonset AAD schemes that can be obtained from UIUE. But now we can also look at alternative RPRP constructions and plug them into these constructions and obtain new AAD schemes or nonset AAD schemes. And finally, we think the nonset AAD abstraction is also useful because it provides a clean boundary between for understanding orders in channels, and this boundary separates security that is mostly provided by the nonset AAD and the channel functionality which is obtained from the nonset processing algorithms. So that concludes my talk, and thank you very much for your attention.
All right. Any questions from the audience?
Thanks a lot for the nice talk. I just, one thing that I wondered is in this separating construction. So this is a real world construction, right? That's supposed to be used. Is that correct?
The channel construction?
The separating construction between rugged PRP and SPRP.
Oh, okay. So the UIV construction, right? Yeah.
Is this something that's used in the real world, right?
Yeah. I mean,
yeah. So in that case, I was just wondering, like, it has these two components: the variable output length PRP and the cipher, right? Mm-hmm. And you can remove one instance of the cipher. So, like, I was just wondering about the basically the influence of the two components on the runtime. Like how much runtime you can save with this?
Okay. Yeah, that's a good question. So in particular, so for example, one thing that made it clear is that when you have 3 layers, you'd need at least 2 passes over both enciphering and deciphering over the data. When you remove one, you will have a similar effect that you have with GCM SIV or SIV, essentially that enciphering will require 2 passes, but deciphering will require only 1 pass because the 2 can be parallelized together. And here, I mean, it's not just to realize the tweakable cipher. You normally need a block cipher or a tweakable cipher with a fixed tweak size, but then you need something else to handle the variable length tweak. And that's normally like a universal hash function, right? So it's not just one block cipher call, it's also computing that tweakable cipher, that universal hash, which in the case of GCM is normally G hash.
Okay. So basically, if I understand correctly, what you're saying, actually the cipher is the more expensive thing here, and the variable output length PRF is the cheaper thing.
The variable PRF tends to be the most demanding, but if you have like 2 tweakable ciphers, you can't parallelize them with the variable output PRF, right? So then you need to do another pass over the data.
Right. Thanks.
Yeah.
All right. Looks like there are no more questions. I think it's time for lunch, but maybe I'll allow myself to make one important announcement. You might be used from the past to the fact that the conference ends now, but just a reminder, we're not ending now. There's still one session after lunch, starting at 1 until 2:15, and that's going to be the official last session of the conference. So hopefully many of you will be there. Thank you.